Hi, welcome to section 10.4 and 10.6 notes. This is on perimeter and area of similar figures, as well as circles and arcs. We'll do more with circles later in the chapter and also in chapter 12, but this is a good start to that. So first thing here is if the scale factor of two similar figures is a over b, so a fraction. We talked about scale factors quite a bit in chapter 7 when we were talking about corresponding sides of figures being proportional to each other. So a scale factor, if two figures are similar, then we can write a ratio or a fraction of two of those corresponding lengths, and that would be the scale factor. So the ratio of the perimeters would also be A over B. If you think about the units of a length of a side of, say, a triangle, it would be just meters or inches or feet. And so the perimeter, if you think about perimeters, just distance around a figure, the units are still inches or feet or meters and so forth. The units for perimeter are not squared or cubed or anything like that. It's same as a regular side length. But the ratio of the areas, like we've just been doing the last few sections, anytime we're finding area, our units are squared. So same thing, the ratio of the areas would be a squared over b squared. Okay, so again, it's still related to the scale factor, related to the ratio of the perimeters, that a and b, but those dimensions end up being squared when we're referring to area. So a couple examples of that. It's telling you that in examples 1 and 2, that the figures are similar to each other. And so it says, what is the ratio of the perimeters and the ratio of the areas? So in terms of the perimeter, then we know that we can take two corresponding side lengths, which they only gave us one pair of corresponding side lengths, and we can write that as a ratio 4 over 6. And then if we can reduce it down, we would reduce that down. Okay, so again, that's our A over B, two lengths and reduce down if needed, and that would be the scale factor as well as the ratio of the perimeters. But if referring to the area of these figures, then that would be a squared over b squared, like we just talked about. So it would be our, we could take the scale factor or the ratio of the perimeters and square both of those. So we can either square the 4 and the 6, okay, or we could go ahead and square the reduced down version of that 2 over 3. Either one is going to give us the right answer. Squaring the 2 over 3 is going to get us the answer faster. We're not going to have to reduce down our fraction after squaring the 4 and 6, but either way is fine. And in this case, we end up with 4 over 9 either way. Okay. The same type thing on number 2 for the perimeters. Again, the ratio of it helps you to refer to it as A over B. That's fine. But we've got 12 over 9. And again, that can reduce down since 3 divides evenly into both. We reduce that down to 4/3. Okay, the ratio of the areas, like we already said, is A squared over B squared. So again, I could do 12 squared over 9 squared and then reduce that down. Or I could just go ahead and do my reduced down version, 4 squared over 3 squared. And when I do that, I get 16 over 9. That just gives me my answer sooner. Okay. Then if we look at examples 3 and 4, it says that the figures are similar to each other. The area of one is given. Find the area of the other figure to the nearest whole number. Okay, so in this case, first we're going to start off like we did a moment ago. We know that the scale factor is A over B, which is 3 over 6, which I can reduce down to 1/2. Okay, so I know that the ratio of the areas then is A squared over B squared, which again, I can square the 3 and the 6, or I can square the reduced down version, which is the 1 and the 2. Either way is fine. That's going to get me my answer quicker. But either way is fine, and I end up with 1/4. So I know the ratio of the areas is 1/4, and now I'm going to use that to help me figure out the missing area that they're asking me for. I can set up a proportion. So I can take my ratio of my areas, 1/4, and then it says the area of the smaller parallelogram is 6. So that's going to be corresponding with the 1. And so now my unknown is the ratio of the larger parallelogram, which I'm going to call x. If I cross multiply, 1 times x is x, 4 times 6 is 24. I want to make sure I put units with my answer, and that's going to be inches squared. That didn't turn out very well. I'll try that again. Inches squared. So that is my area. Okay. Same type of thing on number 4. We can say, okay, our scale factor is a over b, which is 12/18. And 6 divides evenly into both of those. And so I end up with 2/3. Okay. My ratio of my areas, it would be a squared over b squared, which again, I can square the 12 and the 18, or I can go ahead and square my reduced down version. It's going to get me the answer quicker, and I get 4/9. Okay, so now I'm going to use that 4/9 in a proportion. So I've got 4/9 is equal to, now it says the area of the larger is 121. So I know the larger corresponds with the 9, so it's got to go in the denominator. The unknown is the area of the smaller one, so I'm going to put the x on the numerator. And now when I cross multiply, I get 9x is equal to, let's see, 4 times 121 is 484. And then if I go and divide by 9, I get x is equal to 53.78. But my directions on this one happens to say to the nearest whole number. So I'm going to go ahead and round that to 54. And I'm going to put units, and I'm going to put meters squared because I'm looking for an area. Okay. All right. Now we're going to change gears a little bit. Down here, we're just referring to different parts of this circle that we see. So the first thing it's mentioning is a semicircle. A semicircle is exactly half the circle. And so if we look for the semicircles in this particular picture, we're going to name them with 3 letters and put an arc symbol on top. So we're going to name all the options we see. One of them goes from A to C to E. So I'm going to say A, C, E. And I have to have 3 letters, and the A and the E have to be the 2 endpoints of the semicircle, and then I'm just naming one other letter on that semicircle. Another one I can see is a DE. Okay, but if I go ahead, I guess let me try another color. I can show you some more of them. Another one that I can see is CED. From here to here. Okay, and another one I can see is DAC from here to here. Okay, so 4 different ones that we can see here. And it doesn't matter if you have it backwards for me, like the first one, if you have ECA, that's fine. And I have ACE, they mean the same thing. Okay, next are the minor arcs. So let me erase these semicircles. Okay, and a minor arc is going to be smaller than a semicircle, so it's something less than 180. A semicircle is exactly half the circle, so that is 180 degrees. We already talked about the other day that 360 is all the way around the circle, so half is going to be 180. Basically, a diameter is what kind of cuts the circle in half, and creates those semicircles. A minor arc is smaller than a semicircle, so it's going to be something less than 180 degrees. And we're going to name a minor arc with 2 letters. So I can see one of my minor arcs would be AD, just 2 letters with the arc symbol on top. Another one would be AC. Another one would be CE. And the last one would be ED. Okay, again, if you have yours written backwards from mine, DE or EC or CA or DA, that means the same thing. Okay, the last type is a major arc. So a major arc is something greater than 180. And we're going to use 3 letters to determine it. And it says name the major arcs that contain point A. Okay, so again, we want to name something that is greater than 180. So ACD would be one, from A all the way around to D. Okay, so ACD. Now someone else might call that same exact arc AED. Okay, kind of look at that. Either those are talking about the same thing, so I don't want to name those as 2 different arcs, but I could call it either one. Okay, another one would be CEA. So from C to E to A. Okay, someone else might call CEA CDA, and we'd be talking about the same thing. You could always also have the backward version of what we just said here. Okay, another option would be EDC. So from E to D to C all the way around. EDC would be the same thing as EAC. Okay, and then the last one it would be let me go back to the blue here. The last one would be DAE. I'll just do that right on the circle. DAE. You can see from here to here. And DAE. If someone else called that DCE, we'd be talking about the same thing. Okay. So major arc again is greater than 180. All right, from there, it is mentioning arc measure. So the measure of a minor arc is equal to the measure of its corresponding central angle. So a central angle in this particular picture is like angle RST, if you want to put that as an example. Okay, and so we can see that angle RST is a central angle, and we can see that the measure, underline central angles. That's what that is. And we can see the measure of the central angle is equal to 50 degrees. Okay. And so the measure of the minor arc right there is also going to be 50 degrees. The central angle and the arc are the same. It says the measure of the major arc is the measure of the related minor arc subtracted from 360. And you can see the work for that over here. But basically, it's just showing you that this arc from here all the way around to here is the 360 minus 50, which is 310. Okay, so I can say, that the measure of TQR is equal to 310. Okay. I'm not going to put that by the picture if that's helpful. And the measure of a semicircle is 180. We already mentioned that a moment ago. All right, so if we use that information to find some of the missing pieces here, then it's referring to circle O. And again, referring to circle O because O is the center of the circle. So that's how we're going to name the circle. BC, we can see from here to here, this particular arc is the same as what this central angle is. So that would be 32 degrees. And on number 9, the measure of BD from here to here would be 32 plus 58. You can add arcs together, and that would give you 90 degrees. Okay, the measure of ABC, let me switch the color here. So A to B to C, from here to here, we can see that arc meets up with the diameter CA, so it's exactly half the circle, so we know that's 180. And then the last one is AB. So I can see that AB goes from here to here. So half the circle is 180. This little arc is 32. So I can go 180 minus 32, and that gives us the 148. Okay. And then the last little bit is the length of the arc of a circle is the product of the ratio of the measure of the arc over 360 and the circumference of the circle. So you can see the formula here, the length of AB, and that's just telling us how long it is from here to here. Not the measure of the arc, but the length of the arc. If you think about the circle being a piece of string, and if you think about all the way around a circle, kind of the perimeter of a circle, we call that the circumference. And if we want to know what portion of the circumference AB is, then, we're basically saying how long is that piece of string. So we basically just wanted to figure out how many degrees that arc is, the measure of that arc over the total amount of 360, and then we're multiplying that by the circumference, which is 2 pi r, 2 times pi times the radius, or you can think of the circumference as diameter times pi. Either way will get you there. So if we look down here to solve, let me keep our formula that we can see here. We can see what is the length of the arc, leave answer in terms of pi, and then what's arc xy. So it's referring to here to here. So in terms of the length of arc xy, our formula is the measure of xy over 360 times, again, we can think of it as 2 times pi times r, or we can think of it times diameter times pi. So either way works there. If I want to think of it as diameter times pi, then my measure of the arc, if this is a 90-degree angle, the measure of the arc is 90. So I've got 90 over 360 times the diameter, which is 16 pi. Okay. And in this particular case, if I want to go ahead and reduce the 9 over 360 down, I can. I know 90 goes into 90 one time, 90 goes into 360 4 times. So if that's helpful to you, you can go 1 over 4 times 16 pi. And if we think about 1/4 of 16 pi gives us 4 pi. And our units here are inches. If we're talking about a length, again, we're not going to have squared units. We're going to have plain units there. It says leave it in terms of pi, so that's why we're not multiplying by pi. If it did ask us to round to the nearest tenth, we would want to use the pi button on our calculator, not 3.14, because that would keep it more accurate. Unless the directions specifically say use 3.14, you would use the pi button on your scientific calculator. But in this case, since it says leave in terms of pi, that's why we're doing that. Okay, on number 13, if we go ahead and do that, we've got length of arc YPX. And we can see Y to P to X goes all the way around here. And we've got the measure of YPX over 360 times the circumference. So like I said, over here we use diameter times pi. You can also use 2 times pi times r. I'm showing you either way it works. They mean the same thing. So YPX is 240 degrees over 360 times 2 times pi times the radius we can see is 15. Okay, if we get that simplified down, if you'd rather multiply all this in the calculator at one time, you can go 240 times 2 times 15 equals divided by 360, and that will give you 20 pi. But again, if you'd rather kind of simplify down first and then multiply, that would be fine as well. And in this case, you get 20 pi centimeters. And again, a length of the arc is going to be plane units, not squared, not cubed. All right, that is it for 10.4 and 10.6. Let me know if you have any questions.